A warm welcome you all in my presentation whose title is Enhanced Droop Control Technique for Parallel Distributed Generations in AC Microgrid. Among the primary control techniques, Droop control technique is the widely accepted technique and commonly used in the microgrid control. Droop control facilitates the proper load sharing among DGs according to their ratings by making adjustment over the output frequency and voltage. It has various advantages like first, no communication channel required among the DGs. Each DG can operate individually. Second one, easy plug and play operation of DG. We can add or remove the DG without changing the controls of rest of inverters. And the third one, it is easy to implement. Only the droop coefficient is required to calculate and implemented using the gain block. And the last, fourth one is accurate active power sharing. And the derivation of droop equations comes from the power flow control theory, where we assumed the line impedance to be inductive in nature and a too small power angle, which states that the active power flow depends on the power angle difference and the reactive power flow depends on the voltage magnitude difference. The droop equations in islanding mode, where each DG is operated as a master controller R, omega is equal to omega star minus NPP and V is equal to V star minus MQQ. Using the droop equations, we can make the following droop curves. First one tells the relationship between active power output and frequency, and second one tells the relationship between reactive power output and voltage, where omega star and V star are the no load frequency and voltage respectively. NP and MQ are the droop coefficients. P and Q are the measured active and reactive power output at the inverter side. The schematic representation of conventional droop control technique implemented in inverter control is shown in figure 2, where I0 and V0 are the measured output current and voltage of inverter respectively, which is given to the PQ calculation block, which provides instantaneous power output. Then the first order low pass filter is used to get the average output active and reactive power. And further, the droop equations are implemented using the gain block, constant block and summation block to get the reference frequency and voltage set for the controllers of inverter. However, conventional droop control has certain disadvantages like first one, droop control unable to provide damped responses so that the oscillatory modes of the controller can be damped and the better dynamic performance is accomplished. Second one, droop control has power sharing limitations. When there are mismatches between the inverter's physical parameters like output filter components and power line impedances that connect converters to the PCC. The additional reactive power provided by the inverters because of the improper sharing don't allow the inverters to supply the maximum allowable real power. And to mitigate the constraints of conventional droop control, several improved droop control methods have been presented in the past, such as generalized droop control based on ANFIS, droop control based on virtual impedance, droop control method for high voltage microgrid, double derivative based droop control. Amongst all the droop control techniques, the generalized droop control gives proper voltage frequency control. However, it extremely relies on the lines or cables specifications connected between the inverter interface, distributed generation and load. And the second one, droop control based on ANFIS, artificial narrow fuzzy interference system, mitigates the problem of calculating line parameters. However, it increases the complexity of controller. And the third one, droop control based on virtual impedance achieves accurate active and reactive power sharing by adding virtual resistor and inductor, but it increases voltage drop, additional power loss, thus decreases efficiency. And the fourth one, as the name says, the droop method for HP microgrid is only applicable for the microgrid having line impedances inductive in nature. Double derivative based droop control provides power sharing with damping attributes, but it implements through the similar transmission network. This may not be true in the practical consideration, which may lead to improved reactive power sharing between the controls. Therefore, in order to address the gaps in the existing Droop control strategy, a novel Droop control technique is proposed to achieve the accurate active and reactive power sharing and maintain the frequency and voltage magnitude of load side at the rated value. The structural diagram of the proposed Droop control strategy is shown in figure 3, and the corresponding Droop equations are given as equation 1 and 2. The derivative term in the active power loop is added to the conventional Droop, which improves the transient response and decreases the frequency deviation. On the other hand, the PI term and the root mean square value of the inverter output voltage in the reactive power loop are added to the conventional Droop. That minimizes the effects of line impedance mismatch, achieves accurate reactive power sharing among parallel connected inverters, and controls the frequency and voltage deviation. The microgrid model used to implement the conventional Droop technique and proposed Droop technique is shown in figure 4. The source of power in the grid are two direct voltage sources that each represent PV panels and associated energies to the systems. Since the voltage magnitude of the generation unit in a rare situation will vary according to the weather conditions, a DC-DC closed loop boost converter is needed to transform the voltage into the required level for the inverter. The main focus in this paper is the inverter control. The controllers give a voltage reference to a pulse width generator which controls the inverter's usage. The LCL filter is used at the output of inverter to obtain a nice sinusoidal shape voltage and current waveform before the transmission line brings the power to the load. The line out of the two inverters are of the same type but varying length. Different line helps to understand the effects of different line impedances on reactive power sharing in the conventional Droop control technique and the proposed Droop control technique. The load is common for both inverters and is assumed resistive and inductive. Since the main focus of this paper is the inverter control, here figure 5 represents the Droop control method of the voltage source inverter. It consists of three controllers: first Droop controller, second voltage controller, and third current controller. The first part of the chain is the Droop controller, which gives a reference to the voltage controller based on the measured power output. The second part is the outer voltage control loop, which converts this reference voltage into the reference current using the filter capacitor voltage and the filter output current. The output of the voltage controller is the current reference to the current controller, and this inner current control loop gives the final reference output voltage using the filter capacitor voltage and the inverter output current. This final reference voltage generated by the current controller, which has to be followed by inverter, is used to generate the pulses using sinusoidal pulse width modulation technique, and these pulses are fed to the gate drives of inverter. Simulation results depict the performance of enhanced Droop control technique compared with the conventional Droop control technique through the simulation performed in MATLAB Simulink. A fault is injected at t equal 2 seconds and removed at t equal 2.2 seconds to see the robustness of enhanced Droop control technique. Figure 6 shows the waveforms of the reference frequency provided by the enhanced Droop controller and the conventional Droop controller to both inverter 1 and inverter 2. The first figure is for inverter 1 and the second figure is for inverter 2. Blue one is for the conventional Droop and the red one curve is for the proposed Droop. And from the figure it is clear that the proposed technique not only provides the constant rated frequency but also adds virtual inertia to the system. Emulation of virtual inertia effect can be seen by the behavior of frequency characteristics during the fault. The active and reactive power sharing through the DG by the conventional technique and the proposed technique is shown in figure 7. The first figure is for active power and the second figure is for reactive power. Here the green and black curve shows the active power and reactive power sharing by the DG1 and DG2 respectively in the case of conventional Droop technique, and the blue and red curve shows the active power and reactive power sharing by the DG1 and DG2 respectively in the case of proposed Droop technique. This figure tells that the active and reactive power sharing improved remarkably with better transient response. The output power from the DG has increased since the operating frequency and voltage has restored in the case of proposed Droop control technique. This figure shows the comparison of RMS value of phase voltage obtained at the inverter output side for the both Droop control technique. The first figure is for inverter 1 and the second figure is for inverter 2. The red one curve is for the conventional technique and the blue one curve is for the enhanced technique. It can be observed from the figure that the proposed control technique increases the RMS output voltage inverter so that the rated output voltage obtained at the load side after certain drops through the transmission line. This result indicates that the enhanced Droop has zero voltage regulation and has successfully restrained the trade-off between reactive power sharing and voltage regulation. Simulation results shows that the restoration of the rated frequency of both inverters and improves the reactive power sharing between the DG inverters by proper selecting the control parameters. The proposed Droop control, unlike the conventional Droop control, improves the transient response and provides virtual inertia during various contingencies. Finally, the conclusion is that this paper proposed the novel Droop control technique to properly operate the parallel connected DG inverters in the AC microgrid, and this improved Droop control technique is able to mitigate the constraints of the conventional Droop control technique. And the future work includes the testing of the proposed control technique based microgrid in the real-time simulation platform to ensure the robustness of the controller during various contingencies. These are the key references used for the paper. That's all. Thank you.